I'm Lee Hively. I'm Senior Research Staff at Oak Ridge National Lab. We began this work in 1994, and I'm going to explain first the motivation for the analysis, how it works. I'm going to show some real examples. I'm going to explain the status of the technology, and I'm going to talk about the conclusions. So a high-level explanation of the problem is that one has adverse events hidden in real data. Those data involve some sort of condition change, but it's hidden amongst very noisy, very complex data, and we set for ourselves a very high goal. Namely, that we wanted to be able to quantify that change using a practical technology. Namely, it was to be fast, real or near real time, accurate, so we wanted to maximize the total true rate, and we wanted it to be a portable device. You don't want this having to be run on a high-performance computer. So here is a 50,000-foot view of how this technology works. We begin with what I call process indicative data. In the case of the example that I'll use, that's brainwaves, scalp brainwaves from the surface of the scalp. It could also be motor power or motor current, vibration or acceleration. We do a data quality check that avoids the garbage in, garbage out syndrome. We remove irrelevant artifacts. So in the case of brainwaves, that's an eye blink. Every time you blink your eye, the brainwaves are superimposed on that eye blink. In the case of electrical data, that would be the sinusoid in the data. We then capture from the artifact filter data a signature of the base case. Now, base case here is representative of the nominal dynamics or the baseline dynamics. We then also subsequently capture test cases. So these are cases that we know may or may not be different from the baseline, and we calculate a dissimilarity between the two. This is based on theorems, which I'll explain. And we then can indicate forewarning by threshold crossings in these dissimilarity measures, several successive occurrences of those dissimilarity measures above a threshold. So this is a sequence of slides that is intended to explain how the data are analyzed. One begins with a long stream of data, and it's divided into segments or intervals. Each one of these intervals I call a cut set. The beginning of the data we use as the baseline, and subsequent data are the test cases. So there are endpoints in each of these cut sets, and in the case of brainwaves, I'm calling that EI time TI. And here's a snippet of real brainwave data. And what you see here is this is an eye blink. And so what has to happen is we apply the artifact filter to remove that eye blink, which is the green, and subtracting the green from the blue, one gets then artifact filter data, which I call GI. So that this filter is not a mystery. The way it works is that over a window of points, one fits a parabola, and then one takes the center of that parabola, the central point in that window, as the estimate for the artifact. And this is what the artifact filter data then look like after the subtraction. So we then take this data and we symbolize it. So there is some minimum in this data and some maximum in this data. And the symbols, the rest of the symbols, and we then convert those into these discrete values. So the number of those symbols may be a small number, 3, 5, 7, or some other smallish number. We then create what are called phase-based states. So there's a theorem here, and I've labeled it Taken's theorem. This is another name for this theorem is the time delay embedding theorem. The values of SI are formed into a vector in the normal algebra sense of the word. So SI is the first component, SI plus some lag is the second component, SI plus twice that lag is the third component, and so on. This is a d-dimensional vector. This is a phase state, and then the dynamics from one state to the next are indicated here, so one has a state-to-state transition. So in the jargon of networks, these are nodes, and this linkage between the states are links, and that forms a network. In graph theory, mathematicians have theorems which allow one then to form a graph. So graph theorems are well developed in mathematics, and this is a real graph with nodes and links based on real data from these brainwaves. So this is an example of what a real graph looks like. So what does one do then with this abstract object, this graph? So I have to first tell you that there are a lot of free parameters here. There are the number of base cases here. There are the number of points in the cut sets here. There is the half-width of the artifact filter here. There's the number of symbols, the number of dimensions in this phase space. There is the lag associated with this vector, and there is a lag associated with the state-to-state transition. So we then take these graphs and we compare them. So we compare the nodes, so we have unique identifiers for each node, and we have unique identifiers for each link. And we compare the nodes and the links between the first graph and the second, between the first graph and the third, and so on, through all the combinations, unique combinations of these graphs. And that gives us then an average similarity or dissimilarity between these base case graphs. We do the same thing for the links. And that then gives us an average and a standard deviation for those nodes and links which are dissimilar, because it's the dissimilarity that we're looking for in these data. And we then can normalize the number of nodes or links to this average, and this is standard deviations from the mean. And this just says in words what I've just said. We have different nodes and different links, and we have topological invariance due to the graph theory. We also have metrics. Okay, we now have a long series of data for each of the event and non-event data cases in the case of epilepsy. And the question is, how do we get forewarning? And the way that's done is that we calculate these dissimilarity measures, and we ask, do we see several successive occurrences of these dissimilarity measures above a threshold, and that gives us forewarning. And clearly, what one wants to do is to maximize the true negatives, that is, no forewarning when there is no event, and we also want to maximize the true positives, which is forewarning when there is a real event. Inversely, we want to minimize the false positives, which is a forewarning when there's no event, and we also want to minimize the false negatives, which is no forewarning when there is a real event. So also with this analysis, we then get the forewarning time. So the purple locations are when there is an indication of forewarning. The blue is when the event occurs, and the difference between the purple and the blue is the forewarning time, which we tabulate. So this is an example then of how we summarize all those data. We plot the false negative rate versus the true positive rate versus the true negative rate, which is 1 minus the false positive rate. And the ideal is up here in the corner when one has basically perfect forewarning. So now I'm going to show other examples. This is an example for a real gear. So this gear failed, and this is the piece that broke off. The data for this analysis was acquired by the U.S. Army Research Laboratory and NASA. They spent 10 years analyzing that data in an attempt to forewarn of this failure, and they were not able to. So they gave the data to me, and what I found was that there is a threshold in the green here and here. These are two accelerometer channels. The data here were acceleration data, and what one finds is that there is a threshold above which the dissimilarity measure rises and stays above that. And this is the forewarning region. And then there is a second threshold. And when the dissimilarity measure rises above that level, that's an indication of the failure onset. And they were very pleased with that result. So this was an example where the gear was over-torqued by 50%, and it took 4 hours to go from here to the failure. The data were sampled rather rapidly in 1.5 second intervals. So here is another real example. Excuse me. This is a real full-scale bridge in Switzerland. And this bridge was to be torn down, and the civil engineers convinced the authorities to allow them to do some testing on this bridge. And the testing in particular, the red here is an indication that what was done was that this pier was elevated in increments of 20 millimeters, no elevation, 20 millimeter elevation, 40 millimeter, 80, and 90. And then what they did was to apply a thumper to the bridge, and the bridge did this in response. And the question was, could I, from that response data, that acceleration data, see the change in this pier offset? And the answer is that the points in blue are the dissimilarity measures that I got, and the line here is the correlation between that. The probability of that being a random occurrence is at the level of 10 to the minus 4. So this is a summary of many applications. This is a very busy slide, but the intent is to show you that we have analyzed data from Electric Power Research Institute, from a Spanish collaborator, from Penn State University, the Applied Research Laboratory, some more Electrical Power Research Institute, some more Penn State applications. We generated some data. There was a machining center at Y12, and we actually have generated some data from PCs. The various equipment here are large motors, medium-sized motors, small motors. There are also a variety of motor-driven components, for example, a blade, a bearing, a gear, and there are a variety of motor failures here: air gap offset, broken rotor, imbalance, turn-to-turn short, and so on. So the A's here indicate accelerated failures. The S's indicate seated faults, which then led to the failure. And there are two examples here of operational failures. So The machining center was a room-sized machine that could machine a cubic meter of material, and what I was given was data from what was called the W-axis of that machining center, which is the axis that rotated the workpiece in the vertical axis. There was a bellows coupling that failed, and I was asked, could I forewarn of that failure? And the data in that case was motor current. And in all of the cases, we were able to correctly forewarn or detect the event. So the various kinds of data here are power, torque, vibration, stress and strain, acceleration, and timing data from detecting malware on a computer. So the total true rate here is 20 out of 20. And what makes this work is that this is the theorem-based technique that is data agnostic. So given the data that is indicative of what's going on, one can then forewarn or detect the failure. So let me talk a little bit more detail about the epilepsy example. There were 19 channels of scalp data. The sampling rate was 250 hertz. The data sets ranged in length from an hour and a half to a little over 8 hours long. There were 40 event cases and 20 non-event cases, males and females, pediatric to elderly. And in the example I show here, we have a true positive rate of 39 out of 40 and a false positive rate on the non-events of 1 out of 20. We got an R&D 100 award for this in 2005, and that award was for implementing this algorithm on a PDA class device where we received the data wirelessly, analyzed the data on the PDA, and then transmitted the result back wirelessly from the PDA. So here is a summary of other biomedical applications. I just talked about the EEG for warning, EEG epilepsy. We've also analyzed heart attack data, ventricular fibrillation, 4 data sets. We've analyzed human ECG for atrial fibrillation, rat ECG for sepsis. This was an endotoxin exposure. Human ECG for fainting, otherwise called syncope, and pig chest sounds data for breathing difficulty, and the success rate there, again, was 100%. So the intellectual property involved here is 12 patents and 1 pending. These patents span from 1997 to present. So there are now 4 invention disclosures in addition to the patent pending here. So this is a large intellectual property portfolio. So the status of the technology is that there is a high fidelity integration where we have tests in a simulated environment. We forewarn of the failure or the event. The analysis is of archival data, and the analysis is performed either on desktop computers, a PDA, and I now have a student who is coding the analysis in Android on a smartphone. And the analysis is based on theorems, which means that it succeeds for this large variety of applications. So there are lots of other potential applications. This is what I call my twinkles in my eye slide. So I have actually looked at some real earthquake data, and I see what look like forewarnings of the earthquake. I have not been able to get anybody to give me solar storm data, but given the right kind of data, for example, magnetic and electric fields, I think I could predict solar storms. I have a patent on using this technique to compare brain waves from known subjects to brainwaves to unknown subjects, and to use the very same dissimilarity measure approach as an EEG biometric. One can also potentially use this to forewarn a failure in computer disk drives, batteries. So there are many applications where one doesn't want to use an internal combustion engine, but rather a battery. So these are large batteries, and when they fail catastrophically. And one would want to be able to forewarn of that failure. We would also like to forewarn of a computer failure. So typically it's not just the hard drive that fails, but fans can fail and other things, and circuits can fail. So, in conclusion, the technology has a high total true rate given a proper choice of parameters. It's faster than real time. Let me quantify that. So for the EEG epilepsy example, I have 261 wall clock hours of data. I can analyze that data on a palm-top computer, a Celeron class computer, in 1 CPU hour, 1 wall clock hour. So that is definitely faster than real time. The analysis works on PDAs, palm tops, and smartphones. It's a low complexity algorithm. It works on existing hardware and can be ported as basically an app that one would put, for example, on a smartphone. It can be used with commercial sensors, and there are lots of other applications. So the typical kinds of questions that are asked of me at this point, and I'm going to conclude here, are how much data does this technique need? This is a data-hungry method, so I have never had too much data. The amount of brainwave data that I have is 27 gigabytes. The amount of bridge failure forewarning data that I have from the Federal Highways Administration is 65 gigabytes. Monitoring that data is easy, it's fast. The algorithm is very robust, so it's been coded in Fortran, it's been coded in Java, and it's been coded in C. And each of the 3 different languages have been coded by 3 different people. We get identical results in all 3 cases, so we're very confident that the algorithm has been coded properly. So that concludes the presentation. Thank you very much.